Welcome back to this lecture series on pulse width modulation for power electronic converters. So, we have been looking at power electronic converters, particularly DC to AC converters, and how exactly you do the pulse width modulation for them. That is what the whole lecture series has been about. And the overall course modules, just for a quick recap, first what we did was we had an overview of various power electronic converters, where we looked at DC-DC converters, then we looked at DC to AC, and in the DC to AC we had 2-level voltage source, current source, and 2-level, multi-level, and so on and so forth. Then we looked at various applications of voltage source converter in the second module, so such as motor drive, or static reactive power compensation, and active front end conversion, etc. Then we started looking at the purpose of pulse width modulation. Basically, you want to have the desired fundamental voltage and you want to keep the harmonics and their effects low. So, that is the purpose of pulse width modulation. We reviewed the basic things about modulation, such as the Fourier series and so on and so forth. Then we tried working on the pulse width modulation at low switching frequency. That is, we have only a switching frequency like 5 times the fundamental frequency or 7 times the fundamental frequency and so on. How would you go about doing things like that? So, we looked at the pulse width modulation at low switching frequencies in the other module now. Then subsequently, we have looked at the triangle comparison based PWM. When you are generating pulse width modulation, one of the common ways of doing it is triangle comparison. That is, what you have is you have 3-phase modulating signals and you compare them with a triangular carrier, and you compare, and based on the comparison you switch your inverter leg. If you say that your modulating signal is greater than the carrier, then the top device is on, otherwise the bottom device is on, and so on and so forth, as we have already seen. So, today we may have to have a quick look at some triangle comparison methods also, and also maybe space vector based PWM today for the purpose of our talk here. So, we know space vector based PWM is another way of generating PWM signals. So, these two are the widely used approaches for generating them, and as we have discussed, like most methods can be done in both ways, like sine triangle or third harmonic injection, etc. We normally use triangle comparison, conventional space vector PWM, etc., bus clamping PWM, etc. So, these are all, this is basically these two are two different options, like how you go about generating the PWM waveforms. Whereas, we have a class of bus clamping PWM techniques which we call as advanced bus clamping PWM methods, which will require space vector based approach for the PWM generation. So, that is one burden of our the entire course, is that we have been trying to say that space vector PWM is more general than triangle comparison PWM. So, whatever you can do with triangle comparison PWM, you can do it with space vector, but certain things that you do with space vector cannot be done with triangle comparison PWM. So, these 3 modules we focused on how you generate the PWM signals. This is at the low frequency and these two are at the higher frequencies, one by triangle comparison and the other one by the so called space vector approach. Now, after that we have got into the analytical part of that. First is we wanted to see how to analyze the line current ripple. That is, when you are having a fairly higher switching frequency, you really can't do your Fourier series kind of an analysis. There are too many switching angles there, and what we are also interested normally is the RMS value of this current ripple. So, we tried doing some analysis on how exactly you can arrive at that, so that you can evaluate and compare different PWM methods based on the line current ripple. And this line current ripple, as you know, it comes because of the non-sinusoidal components in the applied voltage. Then, after an analysis of that, we have gone into this analysis of DC link current, which is what we have been doing presently. We did it in the last lecture, and we are going to consolidate on that. We had a few discussions on that. We are going to consolidate those discussions and take it to some kind of logical conclusion in this particular lecture. And after that, we would be going into this analysis of torque ripple. That is, when you apply these kind of outputs of an inverter to an induction motor drive, the fundamental component produces of the output voltage produces this fundamental current and fundamental flux, and that produces a steady torque, whereas all the harmonic voltages, they end in generation of certain ripple. So, this is what we will do in the next module, which would be in the next couple of lectures now. So, as I said, here now we are focusing on the analysis of DC link current, and in this there is various things that we are trying to cover. Is we are just trying to cover the relation between DC link current and the line currents, the AC side currents. Now, what I have observed while teaching this course at the Indian Institute of Science and otherwise is that students generally are very familiar with this line currents. They get very quickly familiar with this, because the DC side voltage is fixed and we multiply with some modulating signal and we generate an AC output, and once there is an AC output voltage, you have a load. That load may be an RL load or an induction motor load or whatever, and you have a good harmonic model and the fundamental model available for that. So, it is easy for you to understand what the AC side currents are. So, you know, the moment the PWM output voltage is given, most students are quick at coming up with how the line currents would look like, whereas students normally find it difficult to come up with, to conceive how this DC link current would look like. It is a very important thing, because this is the kind of current that is actually drawn by the inverter. So, that is one reason why it is important, and the other reason it is important is this DC link current has a DC component, which is what it is a measure of the power that is being consumed by the power being converted by the converter. This DC link current has a very major ripple component. So, it is a high ripple component, and these ripple component would flow through the DC side capacitor. So, as you know, for a DC capacitor, RMS current rating is a very important current rating. When you choose a DC capacitor, you need to specify not only the capacitance value, not only the voltage rating, you also have to choose the RMS current rating, and that really comes from the ripple component of this DC link current. And overall, for an understanding of a simple voltage source inverter, it is very essential that we need to link these two, that is to be able to relate the line side currents with the DC link currents. So, that is something we would try to consolidate our understanding in this regard in today's lecture. So, to be able to relate the two sides on the DC link current and the AC side current, what comes in between are the switches of the inverter. So, we are actually going to do a mathematical model for the PWM, which we did in the last class. Like basically we are looking at this DC voltage and certain switching functions. So, there are bunch of 6 switches, 3 pairs of complementary switch. For every pair of complementary switch, we define one switching function. Based on the switching function, we try to derive the voltages, and the inverter voltages are fed to the load model, and then the load currents. The load currents are fed back, and using the load currents on the switching functions, again we come back to the DC link current. So, we had a brief discussion on the mathematical model last time. We may also have a quick review of it now. So, for this we will use switching functions, as I just mentioned a while back. So, what are the switching functions? You basically have 6 switches, as I said a while back, and each switch in every leg they have 2 switches which switch in a complementary fashion. So, you define what is called as a switching function. If, let us say, if switching function is 1, a particular switch is on, or it is 0 otherwise. So, that is the idea behind a switching function. And so, on the AC terminal voltages, AC side currents, and from AC side currents and the switching functions, you can actually go to the DC link current. So, we would have a quick recap on that, and we would deal with this instantaneous and average DC link currents at greater length, and we would also try to come up with DC capacitor current, and we will try and see how an analytical expression can actually be written. For example, DC capacitor current, that is, let us say you have a voltage source inverter and it is being operated at a particular DC voltage, at a particular modulation index, and switching and power factor and so on and so forth. So, under such circumstances, can we come up with an expression for the RMS current is what we would look at. We may not be able to do the details of this derivation, but at least we can see how to go about deriving an expression for this RMS DC capacitor current. So, an expression for RMS DC capacitor current would mean you will have to have an expression for, say, RMS DC link current. So, let us just get started with today's lecture. So, which is the 28th in the series, and we call it DC link current and DC capacitor current in a voltage source inverter. So, we know voltage source inverter, and we just today we want to improve our understanding on these two, which are actually closely related to each other in today's lecture. So, let us just get into this now. So, let us look at a voltage source inverter. So, this is a 3-phase voltage source inverter. As I have said n number of times before, every leg is a single pole double throw switch, and the pole is the midpoint of this leg, and this is connected to the load, which is usually inductive, and the throws of the switch are connected across the DC terminals, and so this single pole double throw switch is realized using 2 complementary switches, and the switches are capable of conducting in both the directions. So, you have R phase leg, you have Y phase leg, and you have the B phase leg, and the load is connected. This is a 3-phase load. So, it is R, Y and B terminals are actually connected here, and the load is not shown here. And so, the load currents are going to flow here. This is the indicated positive direction. So, if IR for example is positive, this is the direction in which current flows. If IR is negative, then the current is actually flowing in the opposite direction. So, and as we also discussed while we were discussing voltage source inverters, we can see how which device conducts. For example, you have a transistor and an anti-parallel diode in the top. You also have a transistor and an anti-parallel diode at the bottom. So, the question is who will conduct when. So, let us say this is the direction of current flowing here, that is from my left to right as shown by the arrow mark here. So, in that case, let us say if the top device has been switched on, the bottom device will be switched off, and the top transistor will actually conduct this current. So, let us say then when the top is switched off and the bottom is switched on, in that kind of a scenario you have a difference in this now. So, who will be conducting? The top transistor can no longer conduct. So, the bottom diode will come into conduction. So, for this direction of current, it would be the top transistor or the bottom diode. For the opposite direction of current, it would be the top diode or the bottom transistor. So, whether top or bottom conducts depends on whether the switching, whether the gating signal to the top is high or gating signal to the bottom is high. Otherwise, whether the IGBT or the diode conducts depends on the direction of the current. So, we have said that this is been required bidirectional current conduction and so on and so forth. We have also mentioned at some point of time that voltage source inverter, any voltage source converter basically means at this pole you should be able to apply either this voltage or that voltage regardless of the direction of current, excuse me. So, this is what we have been now. So, what I am trying to say today is, let us say we are been considering a fixed DC voltage. In actual cases, there will be certain amount of ripple on the voltage, but we are ignoring all that and we are considering it to be fixed voltage now. Then what are you doing? You are modulating the inverter. Basically, you are going to be switching all this. That is, this is switched in a complementary fashion, and the way you switch the R phase, you would switch the Y phase in the same way, except that the gating signals would be shifted exactly by 120 degrees at the fundamental frequency. And the way you switch the Y phase, the same way you will be switching the B phase, except that the B phase gating signals would be switched when I will be shifted by 120 degrees from that of the Y phase. So, this is what we are going to be doing now. As a result of this switching action, so you will get voltages here which will be plus VDC by 2, minus VDC by 2 and so on and so forth. You will get line to line voltages which may be plus VDC or 0 during the positive half cycle and minus VDC and 0 usually during the negative half cycle, and through the load you will have currents flowing, through the AC loads you will have current flowing there now. So, you will have an AC voltage available, and that AC voltage, but not necessarily sinusoidal, it will have a fundamental component plus it will have switching frequency components, and that will drive these currents IR, IY, IB through the load, and which will also have sinusoidal and fundamental, for the fundamental and harmonic components now. So, now we are now trying to say these are the 3-phase load currents. For most of our analysis regarding the DC link current, we would ignore the harmonics part in that, as we will see that part is actually pretty small. So, we would consider, let us say, mainly the fundamental component in doing this now. So, the next question is, if this current IR is what is flowing here, so what is the current through the top device, or what is the current through the bottom device? Let us say what is the current through the top device. So, this IR flows through the top device if the top device is on. So, otherwise it flows through the bottom device. That is as simple as that now. Okay. So, now what is this IDC? It will be this top device current plus that top device current plus this top device current. The sum of all these things is called the DC link current, and please remember in our discussions here we call this as IDC, and this is what is really we call it as the DC link current here. Okay. So, this DC link current, then you have this IS, which is, we use the term S because this comes from the source, like it comes from the DC source now. So, the difference between these two flows through the capacitor current. This current, as you can very well make out, it is going to have a DC component and the ripple component. So, most of the ripple component is going to flow through this, or we are going to assume that the entire amount of ripple component flows through this, and the DC component cannot certainly flow through this, that comes from there now. And this is how the overall things are. So, this is the DC link current, and the DC link current can actually be obtained, as we will show it mathematically, by product of switching function of this current for this leg and that leg. So, let us just look at that mathematically now. So, we will start with what is the switching function as we did in the last class. We just recap here. So, we say that switching function is indicated by S, and whether the switching function corresponds to R, Y or B phase legs is indicated by the subscript R, Y, B, and when SR is equal to 1, we mean the top device is on, R phase top device is on. When SR is equal to 0, we mean the R phase top device is off, that is the R phase bottom device is on. The same thing is valid for SY and the Y phase and the B phase switching functions SY and SB respectively. So, these are the switching functions which we have defined for our convenience. So, the switching function is going to actually indicate, let us say if you say SR1 is equal to 1, SY is equal to 0 and SB is equal to 0, what we mean is SR1 equals 1 means the R phase top device is on, SY is equal to 0 means Y phase bottom is on, SB is equal to 0 means B phase bottom is on. So, this is a way to define the different switches which are actually conducting. So, now you have that here. You can write down your pole voltages in terms of these switching functions now. If it is a SR, if SR is 1, 1 minus 0.5 is 0.5, 0.5 times VDC. So, if the top device is on, you get your pole voltage to be 0.5 VDC. If the bottom device is on, then SR is equal to 0. So, you will get minus 0.5 VDC. So, you can see that it is fairly clear from that. The same way you will get VYO to be plus 0.5 VDC if SY is 1, that is the top is on. You will get it as minus 0.5 VDC if SY is 0 or the bottom is on. The same way about the B phase. So, you have your 3 phase pole voltages. So, you can see that now we have related the pole voltages on one hand with the switching function and the DC bus voltage now. So, there are some expressions for pole voltages. So, the line to line voltages, as we know, the differences of 2 pole voltages. If you are looking at VRY, this is VRO minus VYO. Similarly, VYB is VYO minus VBO, same way about VBR. So, you get the 3 phase line to line voltages now. So, these line to line voltages are actually applied on the 3 phase load, which is not shown in this picture, right. So, let us say you are considering a 3 phase balanced load. So, these are RYB terminals. We have now assumed a star connected load with neutral point N, but this neutral point N is not connected anywhere as we have always been assuming in this course. So, this is actually a 3 phase load, it is a 3 phase 3 wire load, it is only RYB are connected, it is not a 3 phase 4 wire, neutral is not connected, it is a 3 phase 3 wire load. Further, it is a 3 phase 3 wire balanced load. So, like if you apply balanced voltages, they will draw balanced currents. So, for simplicity, let us just consider RL load as we go further, but before that, if the load is balanced, what you can always observe is you can express your VRN, this is the phase to neutral voltage applied on the load, in terms of VRY and VBR, that is given by this equation here. So, VRY minus VBR, the whole divided by 3 would give you VRN whenever the load is balanced. So, similarly, you have VYN and you have VBN. So, you have expressions for this. So, you can now also have the line to neutral voltages for the 3 phase load. Okay. If we are considering an RL load, for example, this VR and VY and VBN are fed to the load. If the load happens to be RL load, as I mentioned previously, this is the circuit equation. So, you can solve the circuit equation, that is dir by dt etc. So, you can integrate dir by dt, that will give you IR, and so once you have IR, you can multiply it by R and subtract from VRN, the whole thing can be divided by L. So, you will have a loop, you will have the first order dynamic system. So, this will be another first order system, this will be another first order system, you can just solve them, they will give you IR, IY and IB. So, these IR, IY and IB can now be used. So, these IR, IY and IB, they come from the load. So, the load, it is not necessarily it is an RL load, it can also be an induction motor load. So, in this case these equations etc. can be more complex, but there are courses and motor drives etc. you would have studied about modeling of motors, induction motors and so on, and you will know how exactly to simulate from those courses. So, those IR, IB, IY and IB from the load has to come back here. So, this is what you are using now. So, now that IR multiplied by the switching function SR is going to give you the top device current. So, if SR is equal to 1, then the top device current is IR. If SR is equal to 0, then the top device current is 0. So, the top device current here is SRIR. Again, what is the top device current here? It is IY multiplied by SY. So, SY times IY. The same way here the top device current is SB times IB. So, the sum of these 3 top device currents is your DC link current, and IDC can be written like this as a sum of this product of switching function and line current now. So, if you see IDC, let us say if SR is 1 and SY is 1 and SB is 0, it is basically IR plus IY, or let us say SR alone is 1, others are 0. So, IDC is equal to IR. So, now in IR you have fundamental component, you also have the harmonic components, and you are considering fairly high switching frequencies. Now, the harmonic components are going to be very low, the ripple part of it is going to be fairly low. So, this IDC expression you will get it as reasonably valid, it will be correct if even if you approximate this IR by its fundamental component, IY also by its fundamental component, and IB also by its fundamental component. So, what we will do here itself is that we will actually consider only the fundamental components to make the calculations easier, because the contributions of the harmonics flowing in R, Y and B, the harmonics themselves will be low when you are talking high frequencies, low meaning low compared to the fundamental component, and their contribution to the IDC is going to be negligible. So, this is the equation for the instantaneous DC link current in terms of switching functions and the 3 phase line currents. So, we go further now. So, before we go into studying how the DC current is going to vary, it is better that we take a quick look at the space vector plane. There are about the 6 voltage vector, active vectors and the 0 vector. There are 8 different inverter states. This is when all the bottom are on, this is when all the top are on. So, in these states you have a null vector getting applied. Now, what you have is there are 6 other states, and in these states there are these are actually called active states, as we have seen earlier. So, these active states produce active vectors which are like this, and based on the conventions that we assume, the active vectors are actually of magnitude VDC. As I have also mentioned before, if let us say you use a slightly different kind of space vector transformation, you may have a constant multiplied by VDC, some constant like it could be root 2 by 3 under square root and so on and so forth. So, things are fine. So, for our kind of space vector transformation, these vectors give you a voltage VDC, and for the active vectors all produce voltage vectors of magnitude VDC, but the angles are different, as we have seen before now. For today's context, actually this VDC does not matter so much. We are actually looking at why we want to look at it is we are shortly going to relate the DC link current with the inverter states. The DC link current we have related with the switching functions. If you put the 3 switching functions together, that is the inverter state. So, it is better that we take a look at this. So, whenever the voltage vector is here, that is the voltage vector if the voltage is provided as a space vector. What if the voltage reference is provided as 3 phase sinusoids or 3 phase sinusoids with common mode added? What you do is you transform those 3 phase sinusoids into the space vector domain, and you will get a reference vector. So, if that reference vector happens to be in sector 1, you would normally be applying these two active vectors plus minus minus and plus plus minus, and you will be using this null vector. So, this we call as sector 1 as the region between active vector 1 and 2. We call this as sector 2. Sector is also known as hextant, because there are this divides the plane into 6 portions, that is the region between active vector 2 and 3. So, similarly this is sector 3, this is sector 4, this is sector 5 and this is sector 6. The operation of the inverter is symmetric. As you can shortly see, the DC link current will also actually be symmetric, and it actually will have a periodicity of 60 degrees, as we will see. So, first let us start looking at sector 1 and see how the DC link current is. So, sector 1, as I mentioned, you are going to apply active vector 1 and active vector 2, which are indicated by this plus minus minus and plus plus minus. So, I mean this may be a little cramped, but you can certainly see when it is plus minus minus, you can see R phase voltage is high, Y phase is low and B phase is low. So, the inverter state here, it starts from 1 0 state minus minus minus, that is all VRO, VIO and VBO are negative, and it goes through plus minus minus, where VRO switches positive, VIO and VBO are 0. Again you have this T2, so plus plus minus, right. Then you have plus 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 where all of them are on. So, this is starts from one 0 state, goes through one active state, then the second active state, and finally goes back to the other 0 state. The next sub cycle or half carrier cycle, it will have the reverse sequence plus plus plus, then B phase switches and plus plus minus, then Y switches, then becomes plus minus minus, then R switches and becomes minus minus minus. And if you look at the 3 phase pole voltages, this is how they are: R Y B, B Y R. That is the sequence in which they are actually going to be switching. So, this is just to look at the inverter state sequence, and this is the sequence in which the inverter states are applied by all the continuous PWM methods, wherever your modulation signal is a continuous function of angle. So, for example, sine triangle PWM, third harmonic injection PWM, conventional space vector PWM, etc., will have this kind of sequence 0 1 2 7 7 2 1 0, and if T0 is equal to T7, that is conventional space vector PWM. So, conventional space vector PWM makes sure that these two 0 states are applied for equal durations of time. So, what is actually illustrated is actually for the conventional space vector PWM. So, now the next step is we are going to see when the inverter states are varying like this, how is the DC link current going to vary. That is the reason why we are now having a recap on this. Okay. So, before we go into that, we have looked at as pole voltages. Now, let us just look at them as SR, SY and SB switching functions. So, when you go through this inverter state 0 1 2 7 7 2 1 0, now 0 to 1 transition SR goes from 0 to 1. Again, this is the switching function for Y phase. SY goes from 0 to 1 here. Here again SB goes from 0 to 1, and then SB switches from 1 to 0. Here SY switches from 1 to 0, SR switches from 1 to 0. So, in this interval R phase top device is on. In these two intervals R phase bottom device is on. The same way about Y phase. Here the Y phase top is on. Here the Y phase bottom is on. So, now this is the inverter state sequence over 2 sub cycles, and this is how the switching functions vary, SR, SY and SB vary. Now, how do the DC link current vary? So, we have just reproduced this state and the switching functions from the earlier graph. Now, what happens? You have minus minus minus. What does minus 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 mean? All the switching functions SR, SY and SB are 0, that is all the 3 bottom devices are on. So, the top devices are off. So, you go by your expression SRIR, that is 0, SYIY is 0, SBIB is 0, and therefore, the DC link current is 0. That is, there is no current flowing between the DC side and the AC side, and that is the reason why you call it as 0 state. During a 0 state, there is no active transfer of power between the DC side and the AC side. So, the load keeps is freewheeling. So, the 3 phases of the load are shorted, and whatever is the stored energy is just kind of freewheeling. There is no power flowing from the DC side to the AC side. So, that is the reason we call 0 state, and this is now what you get here. The DC link current is 0. Then we move on to the active state. What happens in the active state? You have plus minus minus. So, SR is now 1, SY is 0 and SB is also 0. So, you have your SRIR is equal to IR. This is the R phase current. The R phase current is actually a sinusoidal quantity. It will vary over a long cycle, but what are we looking at? We are looking at over one sub cycle. This could be, let us say, 100 microseconds kind of a interval, and this is another sub cycle. This could be another 100 microseconds or so. So, or 50 microsecond and 50 microsecond kind of an interval, while IR can be periodic over 20 milliseconds or 15 or 25 milliseconds, 10 milliseconds, whatever. So, you can see that we are looking over a short interval, and therefore, as I mentioned already, in IR we have ignored the harmonic component. We are considering only the fundamental component, which sometimes we would call as IR1. So, the fundamental component, and the fundamental component is a sinusoid. We are viewing over a small interval of time. So, that looks like a flat line. So, this is your IR. Now, what happens when SY switches up? SR is already high, SY is also become high, SB continues to be low. In this interval, it is SRIR plus SYIY, and SB is 0. So, SRIR plus SYIY is simply IR plus IY, and it is a 3 wire load. It is a 3 wire load. Therefore, IR plus IY plus IB is equal to 0, or IR plus IY is equal to minus IB. So, the current is minus IB. The DC link current that actually, if you look at the B phase current, now R phase current is positive. So, B phase is now, let us say, it is closer to the positive peak, then B phase would kind of be 120 degree ahead of that. So, this is B phase actually negative. So, minus IB would be a positive quantity here. So, you have this current flowing through. When the second active state is applied, the amount of DC link current is different, but there is some DC link current. Once again, after B also switches, what happens? Now, all the top devices are on. So, SRIR is equal to IR, SY is 1, therefore, SYIY is equal to 1, SBIB is equal to IB. So, IR plus IY plus IB is 0, because it is again a 3 wire system, the sum of 3 is 0. So, once again you see there is an inverter state being applied. So, actually if you can look at DC link current, it is very difficult to measure a DC link current. You know why? Because you really can't put a current sensor there. The DC link current we are actually, why we are measuring is, if you just go back to the previous slide and take a look at that, this is between this capacitor and here, and we want the actual parasitic inductance to be extremely low. So, we would all the connections of the terminals of the capacitors and those of the devices have to be connected in such a fashion that the stray inductances are very low. This is because we want to protect the devices from over voltage spikes. If there are stray inductance during di by dt, you will have over voltage spikes, and because of over voltage spikes the devices will get killed, and therefore which we do not want happen. So, you will have a normally very tight design, there will be a sandwich bus bar kind of a design, which will make sure that the stray inductances are very low. And therefore, it is almost impossible to measure current here. You need to make some special arrangements, you use some coaxial current transformer or some such arrangement to really measure the current there. If you measure the current, what you will actually see is how this is. If you actually measure the C, you will see that the current goes through 0 at the start and end of every subcycle. From these zeros themselves, you can make that this is 0 state is being applied, and whenever the DC link current is non-zero, you can know that an active state has actually been applied now. So, this is something which we actually covered in the last class, but this time I just wanted to sink in. So, we are just doing it in some greater amount of detail. So, this is IR and this is minus IB. So, this is again, now what happens in the next sequence, you are going to 7210. So, here again it is 0, here again it is 0, it is minus IB and IR. What is the difference between this subcycle and that subcycle? Obviously, the state sequence is the reverse, it is 0, 1, 2, 7, it is 7, 2, 1, 0. Other than that, you can see that the time intervals have slightly changed, because the 3 phase references are, the reference voltage vector has slightly changed. Under steady state condition, the magnitude of the reference vector will not change, but the angle will change by an angle equal to omega Ts, where omega is your fundamental frequency and Ts is the subcycle time. So, because that angle alpha has changed and the 3 phase references have changed slightly, you have your active vector time T1 is slightly changed to T1 dash, T2 would have slightly changed to T2 dash, and similarly Tz would have changed to Tz dash, and now we are calling this TO dash and T7 dash. So, there are some slight changes, that is because the reference vector angle has changed now. Other than that, what is the difference? IR itself would have changed slightly, which is not very visible from this curve. So, you are talking of IR is equal to some Im sin omega t minus 45 degrees, that is, let us say, is your fundamental current now. So, you are now looking at it at some angle, for example, something like omega t is equal to 100 degrees. So, here this angle may be something like omega t is equal to 105 degrees or so. So, there is a small difference that you might actually get here, which I have not shown clearly on this curve. So, this IR and this IR will be slightly different. Again, this minus IB and this minus IB will be slightly different, and remember this minus IB is IR plus IY. So, if you look at it over a 60 degree interval or much longer than interval, you will see this current. If let us say we are talking of unity power factor load, then your current and voltage are in phase. The voltage is in sector 1, it has already crossed the 0, its positive peak. So, the current would have also crossed the positive peak. So, as you go in this direction, if you are talking of unity power factor load, you will find this IR is actually dropping slightly. So, this level will go on dropping. Similarly, if you go a little earlier, you will see that this level is actually going on increasing. So, you can actually see those variations out of this 3 phase currents really here, which I am not showing. I am showing you only 2 subcycles, which is actually a very small duration within this sector 1. Okay. Now, how does this vary with common mode injection? That is, you are generating your reference voltage, you are applying your active vector 1, 2, etc. Active vector 1, 2 time you have calculated, null vector time you have calculated, you have applied them equally, which means actually some common mode injection. You can divide them unequally also, many ways. So, T0 can be 0.1 Tz, T7 can be 0.9 Tz for example. So, which that is, you can divide this 0 vector time in different ways, which is equivalent to adding common mode voltage to all the 3 phases. So, if you are MR, MO, MB are your 3 phase modulating signals, you can add some MCM, some small quantity to all the 3 of them. So, what will happen now? As we have already seen, if a small component is added, for example, then all the switching will actually shift to the left by equal distance. If some small positive value is subtracted, then our negative value is added, then you may see that all of them will shift to the right, but by the same extent. Therefore, what will happen is, here you will see that the sum of this, so it is the same inverter, same DC bus voltage, same modulation index and same load, everything same. So, and we are also looking at the same subcycle. The only difference we are looking at is, we are considering a case where the null vector division is equal, and we are considering another case where the null vector division is kind of unequal. That is, the common mode added here is different, the common mode added here is something else. So, when you do this, you have now done it in such a fashion that T0 has been increased and T7 has been decreased. So, what happens is, you get the same kind of waveform for the pulse, except that this is just shifted a little. This is when T0 increases at the expense of T7. Now, on the other hand, if T7 increases at the expense of T0, you will find this whole thing shifting to the left. So, I have shown that this is shifting to the right. What happens as an extreme case if T7 becomes 0? If T7 becomes 0, then this pulse and that pulse, they come and combine with one another, and you get a pulse of this nature, and within every 2 subcycles you will see one such large pulse here, whereas here you will see one pulse in every subcycle. So, in continuous PWM schemes such as conventional space vector PWM, if you can look at the DC link current, you can actually say what the switching frequency is from that. So, this region from 0 to, because it is going through 0, this is one half of a switching cycle, one subcycle. So, this is actually one complete switching cycle, alright. Now, this happens like this, so it goes around. So, what is the difference? The pulse position, it actually shifts, but does the average value of IDC over the subcycle changes? No. So, whatever is the average value here, the same thing is the average value here also, the same thing is the average value thing also. So, the average value of the DC link current depends on the active vector times, which have not changed as we discussed in the last class. So, this is the active vector time for T1, this is T2, that is not changed. What has changed? Even Tz is not changed. Tz is divided between T0 and T7, that has changed, but Tz is equal to T0 plus T7, that is still same. So, you have the same average values, and also if you try to look at other things, you will still get the same things. So, this average value actually really it does not change for you within this. So, what happens? You can look at the RMS value. This RMS value is not going to change. Why? I am talking of RMS over a subcycle. You are going to square this. This is going to become IR square. This is going to become IB square, and this is IR square multiplied by time T1. This is IB square multiplied by time T2, and this is what you are going to divide by Ts to get your mean square value integrated now. So, here again this is IR square IB square. So, you try to evaluate this RMS value, you will get IR square into T1 plus IB square into T2, the whole divided by Ts. So, the whole thing under square root would be your RMS value. So, this RMS over thing also does not change. So, this is true about this subcycle, this is true about every subcycle which is yet to come and every subcycle which has been crossed. Therefore, what we can actually say is, one thing that we can see is the PWM method, like you add this common mode and all that. So, that changes the harmonics in the line currents, but it does not significantly change the DC link RMS current. So, whether you talk of sine triangle PWM or third harmonic injection, of course, you have the DC bus utilization is different, that is another point. So, but if you look at within their linear range of operation, so they will not actually give you a considerable difference as far as the DC link current is concerned, and it will follow from there that the capacitor current will also, the RMS value of the capacitor current will also not change very significantly. So, what will change? You can see that there is a small difference in the harmonic components. So, the pulses are actually same everywhere, but you can see the angles are slightly different. So, if you actually take a harmonic spectrum, in these cases what they do is they do not use Fourier series, but they use double Fourier series to calculate such things. So, now if you actually look at the harmonic spectrum, you would see that this harmonic spectrum and this harmonic spectrum will be slightly different. That is all that you will, but the overall RMS current does not change very significantly with the PWM method to PWM method. That is one important thing. So, let us go further. Now, we have actually looked at sector 1, this is sector 1. Now, we are going to look at sector 3. Why? We are actually looking at the same thing 120 degrees later. That is all that, the same reference vector, same magnitude, but the angle has been increased by 120 degrees. So, we are now in sector 3, or the 3 phase modulating signals have changed. So, MY is become what MR was before. So, you actually have 3 phase symmetries. So, now what happens is, instead of 0, 1, 2, 3, you 7, you have 0, 3, 4, 7 like this, and you have 7, 4, 3, 0 applied in the other way now. That is, in terms of the inverter state, it is minus, 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 it goes to minus, plus, minus, then minus, plus, minus, and plus, plus, plus. So, you look at the switching functions. The R phase is, it switches last, whereas Y phase switches first, like R phase used to switch in sector 1. Now, Y phase is switching first now. Then B phase switches, then it is R phase. So, the functions SY, SB and SR are like this now. So, what is your DC link current? It is still the same thing, it is SRIR plus SYIY plus SBIB. So, if you take the 0 state, as I mentioned before, the DC link current is 0. Again, what happens at the end? It is plus, plus, plus everywhere. So, it is SR is equal to 1, SY is equal to 1, SB is equal to 1. Therefore, DC link current is IR plus IY plus IB, which is again equal to 0. And how about in between? It is minus, plus, minus. So, the current is equal to IY. And how about this interval? Here it is SY is 1, SB is also equal to 1. Therefore, the current is equal to IY plus IB, which is equal to minus, So, this is IY plus IB, which is equal to minus IR. Okay. So, this is IY, this is minus IR, this is minus IR IY, but you can see the same shape is getting maintained. The same shape is getting maintained. So, you have come 120 degrees later. So, now IR has that value, what IY has that value, what IR had 120 degrees before. So, there is 3 phase symmetry here. So, the roles of the phases have changed, but you can see that the DC link current is not changed. That is, so if whatever DC link current you have in one subcycle now, you will have a very similar DC link current 120 degrees later. This is because of 3 phase symmetry. So, if you want to analyze the DC link current, you do not have to analyze it for the entire 360 degrees, it is enough if you analyze for 120 degrees. In fact, it is not even 120 degrees, it is only 60 degrees as I am going to show now. Now, what I am going to look at is, I am looking at sector 4, that is diametrically opposite from sector 1. So, whatever was the reference vector I considered in sector 1, now I am considering the same magnitude, but the angle is 180 degrees added to whatever it was. So, if I considered something like angle 10 degrees, I mean now I am going to look at 190 degrees, right. So, I am now in the 4th sector now. So, the sequence is, it is like 7 4 5 0 0 5 4 7, it is like plus plus plus, and then it is minus plus plus, minus minus plus, minus minus minus. So, it goes on like this now, and you can see that it switches in the same sequence RYB, BYR. This is just the reverse of what it was. So, once again you look at when you have the 0 state, the DC link current is 0. Again, when you have the 0 state, the DC link current is 0. So, what you have here now? It is minus IR IB. Why it is minus IR? You have SR is equal to 0, but SY is 1 and SB is equal to 1. Therefore, DC link current is equal to IY plus IB, and IY plus IB is equal to minus IR. And similarly, if you look at here, SR and SY are 0, SB is equal to 1, the DC link current is equal to SB into IB, which is equal to simply equal to IB. So, this is minus IR, IB and 0, but you can see that the current pulse, this is same, IDC has not really changed. So, here also you see that the IDC is not changed. So, whatever was your DC link current in sector 1, some 120 degrees later it is the same, and again at 180 degrees also it is same. So, whatever the current was at some angle theta, and theta plus 120 and theta plus 180, they are same. So, that actually means in every sector it is going to repeat. So, it has actually got a periodicity of 60 degrees. So, whatever it was at some angle, 60 degrees later also it is the same thing. So, this actually repeats, there is a periodicity of 60 degree. You can actually verify this mathematically. Now, we are actually trying to work out illustrative examples, and we are trying to understand the problem, because understanding the problem is are a very essential part, and then you can write down the equations correctly, and it is a question of deriving things. So, we are now trying to do it. So, we are taking time to do this. So, you can see that the kind of periodicity you can appreciate, which you can actually do mathematically, which is what we can get started off with. This is an expression which I have said at least 100 times now. This is the instantaneous DC link current. All these are instantaneous quantities. As I mentioned before, in IR, IY, IB, we have neglected all the ripple of the harmonic components, and we are considering only the fundamental components, and SR, SY, SB are instantaneous switching functions. So, they are discontinuous. The moment it switches, 1 becomes 0 or 0 becomes 1. So, this is how it is going to be, and you get IDC. IDC will also be a discontinuous function of time, because SR, SY and SB are discontinuous functions of time. On the other hand, IR, IY, IB are continuous functions of time. So, the first averaging that you can do is over a subcycle. What you do is actually over a subcycle. One way to look at it is like what we did before. You can look at whatever is this current. For example, if this is your minus IR can be multiplied by T4 plus IB multiplied by T5, the whole divided by Ts is an average value of this DC link current. This is looking at the vector times, the active vector times and the null vector time. The other way to do that is look at them individually. Do it in a per phase basis. You are not looking at the inverter state totally, but you are going by phase by phase. So, IDC, it has these 3 contributions from the R phase stop device, Y phase stop and the B phase stop device. Now, if you average this IDC over a subcycle, we call this IDC average. So, what has been done? This has been averaged over a subcycle duration, that is IDC average. So, if you average all these quantities over subcycle duration, IR does not change at all, because subcycle duration is very small. It is Im sin omega t, and let us say it has got the time period is something like 20 millisecond or 25 millisecond or 30 millisecond now. Whereas, the subcycle duration we are talking of is something like 100 microsecond or 50 microsecond. You can see it is much smaller than that. So, now this IR is practically is a constant. So, what you do is you are actually averaging SR. So, SR is sometimes 1 and it is sometimes 0, and the average of this SR is actually the duty ratio DR. Similarly, the average value of SY over the subcycle is the duty ratio dy. So, it is the duty ratio of Y phase stop device in that particular subcycle. Similarly, this SB, when you average it over a subcycle, it gives you dB, and therefore, your IDC average averaged over a subcycle is like this. So, what this is the product of duty ratio and current or the fundamental current. So, this is for one particular phase, the same thing is added for all these 3 phases now. So, as you can very clearly see, these 3 phase currents are sinusoidal currents, these 3 phase currents are sinusoidal currents. And what about this dr, dy and dB? They are related to the modulating function. If the modulating functions are sinusoids, then they are also sinusoids. Otherwise, if there is some common mode component, there is some common mode component added now. So, for example, if I am looking at sinusoidal PWM and I want to write my dr, how it is going to be? The modulating signal is going to vary like this. The modulating signal varies like this. So, this may be from plus Vm to minus Vm. So, what happens to the duty ratio? The duty ratio is 0.5 here and the duty ratio is maximum here. It is 0.5 here and the duty ratio is minimum here. So, the duty ratio actually varies about 0.5. So, it goes through it is 0, it goes through a maximum, it goes through a minimum. This is how the duty ratio is as a function of the fundamental angle. So, you can see that the duty ratio can actually be expressed as a function of omega t or the fundamental angle. These are all expressed as functions of fundamental angle. Therefore, you can have IDC average also in that. So, mathematically we know that IDC and IDC average is this has been averaged over a subcycle. What are the actual differences? This IDC will have all of switching frequency components. So, some of the switching frequency components will actually be absent when you do this IDC average. So, but it retains all the other components. The major component here would actually be a 300 hertz kind of thing, it will look at this is actually products of sinusoids. So, it is actually pretty interesting. if you are you have two different sinusoids. So, this is 50 hertz and that is 50 hertz. So, when you multiply two different 50 hertz sinusoids, what will you get? You will actually get a DC and you will get a 100 hertz sinusoid. Or if you multiply sin omega 1 t and sin omega 2 t, you are going to get a product, you are going to get sin of omega 1 plus omega 2. Similarly, another sine function which is omega 1 minus omega 2. If you are taking both omega, if you multiply omega and omega, it will be 2 omega and 0. So, the product of this will give you a DC component and a second double frequency. So, the same thing, this will also give a DC. In fact, they are all symmetric, so it will be the same DC. So, you will also have a DC now. So, the DC components will all get added up now. So, the question is about the AC component, and in the case of a single phase rectifier, you will see that there is a 100 hertz ripple. So, here what you would actually expect is actually a 300 hertz ripple, but the 300 hertz ripple would theoretically come out to be very I mean theoretically 0, or it will turn out to be actually very small. Anyway, so this actually this equation is, it takes you one step closer to that, because your dr, dy and dB. So, from now we can see IR, IY, IB can be easily written. We can see how to write dr, dy, dB, though I have already indicated here in this figure. Now, I am just going to write it mathematically. So, if you have dr, you have the modulating signal MR. So, that MR divided by 2 Vp, that where this is the peak of the carrier. The carrier is assumed to vary from plus Vp to minus Vp. So, MR by 2 Vp plus 0.5, that is duty ratio. The same way duty ratio of Y phase can be given as 0.5 plus My by 2 Vp. I am sorry, this should be dB, please correct that, that is got to be dB. So, this is dB. Yeah, thank you. So, this is, so you can see MR, My, MB are 3 phase sinusoids, they are balanced sinusoids. So, dr, dy, dB are also going to be like that, except that they are level shifted by this 0.5. Then what is MR? If you are talking of sine triangle PWM, MR is some Vm sin omega t, and where omega is your fundamental modulation frequency. If f is the modulation frequency, it is 2 pi f, and Vm is the peak value of the sinusoid, and Vm by Vp is what you would normally call as the modulation index. So, MR is your Vm sin omega t, and My would be your Vm sin omega t minus 120, and MB is equal to Vm sin omega t plus 120, but it does not have to be sinusoidal PWM. You may have some common mode also added to that. So, in that case you can add the common mode MCM to all the 3. So, your modulating signal is the 3 phase sinusoids with the common mode added to that. So, you can now mathematically express your dr in terms of MR. So, MR again has been written in terms of this sin omega t and so on. Therefore, dr you can actually express in terms of omega t and the modulation index. So, this is Vm by Vp is your modulation index. Okay. Then, so dr gets expressed in terms of the modulation index and omega t. How about IR? IR gets expressed in terms of Im sin omega t minus phi. This is the peak value of current flowing through the load, and this phi is the power factor angle. We have considered a lagging power factor angle, something lags by phi. Okay. So, IR, IY, IB, as I have said before, the fundamental component alone is shown, the harmonics have been neglected. So, you are now able to express both your dr, dy, dB and IR, IY, IB in terms of omega t and the modulation index and the peak value of current Im, right. So, you can bring all of them together, which I have not really shown. So, from this IDC average dr, IR you can do this. So, the 3 phase currents, they are whatever. If you actually change your modulation signals and so on, you will see that this dr, dy, dB has to be changed accordingly from that now. So, you can get your IDC average over a subcycle. Then what you can actually do is you can average this IDC average over a subcycle over an entire line cycle. I have taken 0 to 2 pi, but you will see that there are several symmetries. So, you really do not have to consider the entire cycle. You can consider 120 degree, or you may consider only 60 degree as we discussed before. If you do this, anyway you have this available as omega t, you take the average value, you get your IDC. What is this IDC? This is the DC component in the so called DC link current, and this is the DC link current averaged over the entire line cycle, and this is really the measure of the amount of power that is flowing into the voltage source inverter, or the power that is being converted by the voltage source inverter from DC to AC. So, this VDC into IDC is the power flowing in from the DC side, and the same would be flowing out of the AC side if you assume that the inverter is ideal, and therefore, you can arrive at this IDC also using the so called input output power balance. What do you mean by input output power balance? Now, this VDC into IDC is the power flowing on the DC side, and the whatever flows in has to flow out, because you assume your inverter to be efficient, 100% efficient now. Therefore, what do you have on the AC side? The AC side you have, depending on your DC voltage and modulation, you have some AC side voltage, and there is a 3-phase load, it draws certain amount of current at certain power factor. So, you can always write that if Vm is your peak phase voltage, Im is your peak phase current, and phi is your power factor angle. So, Vm Im into cos phi. So, this whole thing multiplied by 3/2 would be the AC side power. So, you can look at it from that, and the AC side power and the DC side power you balance, you can come to IDC. So, IDC can be expressed as the AC side power divided by whatever is your VDC. The AC side power is available from DC bus voltage, modulation index, and the load current amplitude and the load power factor angle. So, that is also done, which is what something we discussed towards the end, and I had left it as an exercise for you to be done in the last exercise. So, now what is the important assumption we are going to make? Here we have a DC component, the rest of that are ripple component now. So, what we are going to assume here is, what the source supplies, the DC has to come from there, because the DC component in this cannot flow through the capacitor can take only the ripple. So, the DC entirely flows, but what we are assuming is only DC flows from the source, the entire amount of ripple is flowing through that. So, that way you can link up this IDC and average. So, this IDC is the instantaneous IDC or IDC averaged over a subcycle. If you subtract this capital IDC from that, you are going to get I cap, that is from the instantaneous IDC, you multiply this capital IDC, you will get instantaneous I cap. This is what I am trying to say. So, you can quickly do this, and this is a way of arriving at I cap. So, only the AC ripple flows through that now. So, now this IDC, the DC link current has certain RMS value. You can evaluate it by integrating, squaring this IDC and averaging it over a line cycle and taking a square root under that, that is your IDC RMS. It is the RMS DC link current over a cycle. Now, then you have this IDC, which is actually the average, I mean it is not the average capacitor current, I am extremely sorry. So, it is the average DC current which actually flows through that, there can be no average current through the capacitor, I am sorry about this error. Yeah. So, you have this. Now, if this IDC RMS square, you subtract IDC square from that, you are going to get the ripple part of it, that is the I cap RMS out of that now. So, this is going to give you your RMS current expression. So, this way you can actually calculate, you can see that this is really a function of all these, both of these are actually functions of modulation index, load current amplitude and power factor. So, you will also see this capacitor RMS current is a function of modulation index, power factor and also the load current amplitude. So, it is possible for you to actually derive closed form expressions. It is a little difficult to be done here, but you can actually sit and do it yourself. The major steps we have really covered here, and to help you there are these references now. For example, this is a reference where the 2-level thing has actually been 2-level inverters RMS calculations have been done. This is by Kolar and Round, analytical calculation of the RMS current stress, that is basically the RMS current flowing through the capacitor on the DC link capacitor of voltage PWM converter systems. This was published in IW proceedings in 2006, and this is a more recent work, but it is on a 3-level inverter. So, nevertheless it is useful. So, it is a little more complex than a 2-level inverter, but once you know what a 3-level inverter is, once you know how to calculate the RMS current for a 2-level, it is possible to do this now. So, this is another one which was actually presented in the centenary conference of the Indian Institute of Science in 2011. So, both these are available on the web. So, these references will actually be helpful for you to do these calculations now. So, this I bring my discussions on the capacitor current to an end, and in the next week we will actually be discussing on the pulsating torque. Thank you very much for your interest in this lecture series, and hope that you follow the subsequent lectures also. Thank you.